Society. I'm also on the staff of the museum here, and I'd like to welcome you on behalf of the Science Museum to this seminar on Manchester computers. I have one very brief announcement to make, and that is that Maurice Wilkes is unfortunately unable to be with us today. But he did want me to express his best wishes for the conference, and hope we all have an enjoyable day. Thank you, and I'll now introduce Simon Levington, who is the chairman for the sessions today.
Thank you, Tony. I shall be extremely brief. My job really is to keep these gentlemen to time, because we've got a lot on the programme today. We felt that you'd like to have a chance to hear all the pioneers who have been associated with Manchester computers. They're all eminent, they've all made significant contributions. I won't introduce them in terms of their life history, but some are more eminent than others, and we start with Professor Tom Kilburn. Tom.
Thank you. Good morning. I have met so many people associated with one or other of the machines this morning that it seems very much like a reunion. I especially welcome anybody that I haven't met who was associated with the machines. If you weren't associated with any of the machines, then I doubly welcome you, and we'll try to keep you interested. When Tony Sale asked me to speak and arrange this, I rang up the people who are going to speak, and they all accepted without exception. Of course, each one of them is speaking from his own experience. Apart from suggesting obvious titles to these people, I made no attempt to coordinate the talks. They'll all say whatever they want, so that the coordination is very rough, and each one is something of a personal statement about the work which that person did. We're all conscious that other people could have been invited, and some of those who could have been invited to speak are in fact here today. Jeff Dootil, I've noticed, and Alec Robinson in particular, and there may well be many others. Through circumstances, Freddie Williams can't be here, but he would have enjoyed this occasion. In 1945 and 46, he paid 2 visits to the States to take part in a write-up of radar circuitry, which was going on there, called the 5-foot shelf, and during that visit he visited Bell Labs and saw analog experiments using 2 cathode ray tubes, each one with a metal plate or mesh closely attached to the glass screen, used and tied to an amplifier, and this enabled by capacity charges on the inside of the screen to have an effect on the outside, and the idea was to remove the ground echoes which occur in all radar systems. It was an analog system. When he got back in August 1946, he set up a system to look at this with the hope that something could be done about a storage system. We'd been aware of digital computers for some time then, especially about the Mercury delay line. But of course the Mercury delay line is not immediate access, and there was a chance of making an immediate access store perhaps with a cathode ray tube, and so it proved. The key slide has got lost, and so this rather shaky diagram I did this morning to replace it, he drew a line on a cathode ray tube, which is the blue, and left a gap in it. And these pulses, which are shown, appeared at the output of an amplifier with a gain of about 1,000. Now you can see that this here is the gap, the turning off the beam, the turning off of them here, and the turning it on there. And the turning off of the beam, leaving the gap, is preceded by this pulse, which was called the anticipation pulse. It's obvious that the positive pulse can't be of any possible use whatsoever, because it happens after its event, which is the turn on of the pulse. So a system was devised using this anticipation pulse, discarding that pulse, and when we left TRE, for Freddie Williams was appointed to the chair of electrotechnics at Manchester and invited me to accompany him, and I remained on outside duty as a TRE employee. when we went up there, this single digit had been stored. And my job in the course of taking a PhD was to investigate why these pulses happened, what determined their shape, the best speed for traversing the CRT, and so on and so forth, to learn all about it. It became apparent as I made a raster to cover the whole cathode ray tube of this thing, that this positive pulse was a far superior pulse to the anticipation pulse. It was more uniform over the whole screen, it less affected by the focus, which of course deteriorates towards the edges of the screen. And after about 3 months, the sort of mesmerizing hold of this anticipation pulse was thrown off. And I remember a particular day in which Freddie Williams regretfully said goodbye to this anticipation pulse and said to me, if you want to change it and use the positive pulse, do so. Now, that released a whole new aspect of this storage system, because lots of other systems became possible, more amenable to parallel storage, like defocus, focus, dot dash, 2 dots, and so on. And I can arrange this to get the first slide. Is that it?
Just point it at the
Point it at the back.
Switch number 16 on.
Tony, you better operate it for me. Ah,
There we are, right, yes.
do I get a slide now?
Yes, you do.
There we are. That's old raster of, which is obviously, you can see probably CRT store, in which we talk about not an anticipation pulse, but an inspection pulse. If at the beginning, on a dot here, or the beginning of a dash, you inspect with an inspection pulse, brightening up the beam, you get a positive pulse, the positive pulse you've just seen in the case of a dash, and the negative pulse in the case of a dot. And this enables us to write a dot or a dash as we scan, refreshing this stored program. Now, you may think now we have a cathode ray tube store which is going to be useful, but we're not by any means sure, because whilst the store is a fixed pattern, then this baseline of the signal coming out remains in one place, because the area of this positive pulse is equal to the area of the negative pulse. So this line is fixed. But as soon as you start to write noughts and over ones, or ones over noughts, this line wobbles about alarmingly. And therefore, the only way to make sure you've got a cathode ray tube store is to actually test it with noughts and ones changing throughout the pattern at machine speed. And various pieces of test gear were postulated. And Jeff Tootill and I nearly built them, but in the end, it turned out that it was going to be far easier to build a computer to do the job properly than to actually build test gear. And the only way to be absolutely sure is to see whether it works in a computer. So that's what we did. We set about at the end of 1947, and by the middle of 1948 we had what we called the baby machine, which is that. Now, it's possible, there is the baby machine with the keyboard, the input and output device, similar to a VDU in some minor primitive respects. I'm not sure who took this photograph. It may have been Jeff Tootill, but he was the one who certainly said...
Alec Robinson, I think.
Oh, it was Alec Robinson then. Thank you, Alec. Anyway, it was Jeff Tootill. Who said that it was a picture of Freddie Williams marrying me to the machine. Now, this machine caused a very great deal of interest, and I'd like to read you 2 quotations from a report which Max Newman, who at one time led the Colossus group, and was pinning his hopes on having a machine using the Selectron from the United States, but this store arrived earlier. And he said, at the time, he wrote, "A small prototype came into action about 3 months ago in the electrical engineering laboratory and is thus the first of these automatic general-purpose computing machines to have actually worked." There were several visits. Some of you I know are from NPL. Wilkie Wilkinson came up from NPL, and we had a discussion, I remember, about one address and two address codes and things of that kind, and he was very interested in the machine. Sir Henry Tizard came up, and Newman writes again, in July 1948, Sir Henry Tizard, he was the chairman of the Advisory Council on Scientific Policy, and he was also chairman of the Defence Policy Committee. He says, in July 1948, Sir Henry Tizard saw the machine and considered it of national importance that the development should go ahead as speedily as possible so as to maintain the lead which this country has thus acquired in the field of big computing machines, in spite of the large amount of effort and material that have been put into similar projects in America. Now, that is really a very fulsome statement. However, the most important practical visitor was Sir Ben Lockspizer, who actually, by October 1948, had produced the money to fund Ferranti's in the making of the Ferranti Mark I. And although I was out at the time, Jeff Tootill noticed a man come in through the door without knowing who it was and asked for a demonstration, and Jeff said, the machine's not working, but if you sit down there a bit, I'll get it working and then I'll show you what happens. And they had a cosy little chat, Jeff told me, and it was Ben Lockspizer. So it was a fortunate demonstration which produced the goods. Ferranti's had been interested in the computer before that, and it produced the second magnetic drum for us, starting in February 48. The first was produced by one of the innumerable workshops that existed in the university area of Manchester at that time. And following Ben Lockspizer's visit, and even before, as soon as the machine had actually worked, there was no point in going and keeping on looking at it working. Jeff Tootill and I, aided by Di Edwards and Tommy Thomas, who joined us in September 48, set about making a big machine. And 2 or 3 machines of various powers worked during the rest of 48 and 49. I can't remember the exact periods over which these machines worked, but I can remember that when I was at the Cambridge conference, Dr. J.C.P. Miller was telling me and others that he'd worked out pi to some inordinate number of places, and it seemed a very suitable piece of one-upmanship to ring up Manchester and get them to work it out to a few more hundred places and come down later in the week and boast about it. I don't know if you remember that, David, but it's the sort of thing we are. Well, as I say, this machine worked. It was quite a sizable machine, and it stayed working in the university for quite a time after that, and was used by people like Newman and Turing and 1 or 2 others. In August 1949, Jeff Tootill left the university by mutual consent, joined Ferranti's, and acted as a very important channel for the passage of information to build the Ferranti Mark I. And by November 1949, the specification for the Mark I was in existence. It was complete. And only 15 months later than that, the Ferranti Mark I was being delivered to the university in February 1951. It took, in those days, quite a number of months to install a machine, and it wasn't until June that we had our first computer conference in Manchester, and we invited everybody that we could think of in the country who was working on computers, might work on computers, had a general interest in computers, anybody at all, and we had about as many people as there are in this lecture room today. So it gives you an idea of the scale of the things at that time. The Mark I was, like all those machines, quite difficult to maintain. We had trouble with the machine, we had trouble with the drum, and Di Edwards and I and anybody else who was around at the time were conscripted, Freddie Williams, everybody, to try to keep this machine working. And so the rest of 1951 passed in this fairly pleasant or unpleasant manner, depending on how you want to look at it. People used it, like Sandy Douglas and so on, and we had to ask them to be forbearing, like all those machines in those days. The machine continued to work at the university up to, I believe, 1959. One of our aims was to introduce computers to industry, and collaboration with industry in the making of machines was one step, but the second step was to allow industry to use the machine, and this we did right from the start, charging them some reasonable fee, which I think was £50 an hour for the computation. And so that was the Mark I. Now, you're all aware that it was said around that sort of period in the late 40s and early 50s that only a few machines would ever be required by a country, and so our job could be said to be complete, perhaps in more ways than one. I mean, it was complete in the sense that there might not be anything else to do in computers because you'd done it. And so we went through a phase which didn't last very long, where we were asking ourselves, is that the end? Why build another computer? And this phase didn't, I think, last very long, because there are two arguments I remember, which was that if it were true that each country could cope with two computers, then there were still a lot of countries, and that meant there were a lot of... All right, Tony. Yeah, there were still a lot of countries, so that meant a lot of computers. And the second argument was that, being parochial and thinking about Manchester, if only one computer is needed in Manchester, then it might as well be the best computer. Now, it was clear long before the Ferranti machine actually worked that we could improve on the Mark I. For example, the Mark I, which had been influenced by the pure mathematicians, in that Newman and Turing were the sort of people we were talking to, had special instructions to help pure mathematics, but it was clear by 1951 that pure mathematics would not be the prime use of the machine, and that scientific computing would. So that that was the first thing. To get to a machine which was more suitable for scientific computing, we decided to build a floating point accumulator. Now, I've referred to the fact that these machines were all over the world. The first machines were very, very unreliable, and we wanted to do something about the reliability. And so Freddie Williams, for example, went so far as to suggest that all accumulators should be abolished, that there should be just one circuit, in effect an ANT circuit and a NOT circuit, one NANT circuit, and that everything should be programmed. But of course that slowed the machine right down. And fortunately, I say fortunately, providentially, Freddie Williams became interested in other machines, heavy rotating machines, so that myself and Di Edwards and Tommy Thomas decided to go entirely the other way and build a much more complicated machine with a floating point accumulator. Also, we took advantage by having a parallel cathode ray tube store working into a serial machine. So we used the immediate access property of the cathode ray tube store. And between these sort of considerations, we embarked on a machine called MEG, which became the Ferranti Mercury, and which was 30 times more powerful than the Mark I at about the same cost. I'm going to comment again on the reliability of the machines, which really was occupying our minds. And of course there was a new device which had been invented just a year or two previously called a transistor about. And in the department we were doing some circuit work on transistors. The work was done notably by Barry Chaplin. And he was just making various copies of valve circuits, if you like, using transistors. They were point contact transistors. They were far more unreliable than thermionic valves, but the fact that they were transistors promised that in the future they may be very, very much more reliable than thermionic valves. In any case, they consume very much less power and could perhaps be built into a computing machine. To make the problem reasonably soluble, we decided not to have a cathode ray tube or any other kind of immediate access store, but to simply use a magnetic drum. And so the other person, I'm naming all the people involved. There aren't any people that I'm not naming. I mean, this is the sum of our resources. Dick Grimsdale took on the job of doing this transistor machine with Doug Webb to help him. And so the question, why build a second machine, became much more positive in its answer with a statement to say, let's build 2 more machines. And I pass the buck to Diabet.
Thank you very much, Tom. Depending on how good the speaker is at keeping time, we may or may not have questions after each session. I think we've got just about time for one question to Tom now, before asking Diet to speak. And then I've got the question. At the back, yes.
Very short, quick one. I don't know whether Tom can get the title. I have the back of my memory. I read somewhere, it's a bit lost by it. It was quoted as saying that you thought the country needed one of these machines and possibly another that will stand by. When he said that, I don't know. It must have been about 46 or 47.
I can't tell you whether he actually said that. I just don't know. But he certainly did a remarkable job. I mean, people complain about the slowness of government in the uptake on computer machines. It certainly wasn't true early on. And I was glad to see that it was only, he lived to be, I think, 99. He only died last year. I'm sorry, I can't verify what you were talking about.
Thank you very much. I'm sure there'll be opportunities to say.
In order to keep time, I didn't show my last slide.
Would you like us to quickly run through?
I don't want to run through them because I don't want to delay things, but whoever is next, which is Di, will have to do it with the slide.
Well, I think that's Di's cue to get started. So may we go straight on with Di's presentation.
Wind your I'll wind Tom's diagram off and start with some quotations from users. Now this is going back a few years. The first one, August 1960, from a paper, is Cruikshank, and if I just pick up some of the comments, he says, it's the first serviceable computer to be built which had both an adequate fast access store and a large capacity magnetic drum. It was thus very well suited to crystallographic calculations. I think in saying that, you must remember that prior to the advent of digital computers, crystallographers were stalled, really, in their, the theory was well known, but they were stalled, really, from working out their structures. And so the following comment says that they were able, for example, in the period 51 to 58, to do something like 40 crystal structures on the Mark I. And I want to just pick up another point here. The total machine time, 1750 hours, 250 hours were wasted due to machine faults. That's about 14% of the time they took. And if you bear in mind there was about another 10% of time, which was daily routine maintenance in those days, you can see there was a fair stretch of machine time went to waste, so that reliability was really a problem. Another comment, this time also a crystallographer, Mills, and here you pick up the comment about the floating point, that it's relevant to Mercury, still the same date. So Mercury had been going about 2 years at this time, 2 and a bit years. And as far as they were concerned now, problems of scaling had been overcome. We'd been aware in running the prototype of scaling problems. Gordon Black at that time was designing lenses, and he designed a lens where it didn't matter whichever angle you put the ray in, it came out on the axis. And that, of course, was overflow problems. All the most significant directions were lost. The other point I can make about the store size in relation to the previous comment is, bearing in mind reliability, we weren't likely to make the store of any machine we were going to build, like the Mercury, much bigger, because memory was one of the main problem areas. This is written a lot later, computer story in the meteorological magazine. Met Office were another significant user of our machines, and the first comment really refers to when their Mercury was installed in January 59. The comment about it was put on the inventory with the slide rules and calculators. There's another story about the financial director of ICI, who in 1952 said ICI had never paid more than £50,000 for an instrument and would never pay more. Of course, those were the days before inflation. But of course, A.J. Young, who bought a Mercury for ICI, had to make the case for spending £100,000. So you can see that it wasn't easy, really, to get over these sort of factors. Now, in terms of, Tom has already mentioned FC's comment about wanting to make a simple machine. Fortunately, as Tom says, his interests were taken elsewhere. But if we look at memory sizes, you see the Mark I RAM at 10K bits, the Mark I drum at 650,000 bits. Meg and Mercury had the same size, and on Meg, which was our prototype, it was on CRT. On the Mercury, which was made by Ferranti, it went to core, and the designer of that particular core system, Alec Robinson, is here today. The Mercury drum the drum wasn't that reliable, and so on the Mercury it was made a smaller drum and you were able to have more units, so if the drum went funny you didn't lose everything, it had a bit more flexibility. It was possible to put up to 8 units, but typically again 4 were used. If you think of a 701, which was contemporary with our prototype Meg, sort of 1954 sort of time, they had 7 times the RAM, also on CRT, so it was 72K, but their drums were about 10% smaller, in fact. Tom has already mentioned that we used the CRT in parallel on the Mercury as opposed to serial on the Mark I. Now, in fact, I'd spent quite a lot of my time trying to improve the speed of the CRT and noticeably failed. I mean, we did get it faster, but in the interest of reliability, we really decided to operate it at 10 microseconds rather than push it to its limit. And so by taking 10 tubes, we were able to get 10 bits in 10 microseconds, which of course is equivalent to 1 bit a microsecond. And if you look at this system, you see that if you read out of the store and put it into a delay line, then if you read out with a strobe at a microsecond, then you get 10 bits at a microsecond out here. So this is parallel to serial conversion. And here is serial coming into a register and then parallel flashing it into the memory. And in order to implement this sort of technique, we needed this sort of converter to achieve this, and these delays were provided with electrical delay lines. I have a couple of samples here. These were actually made in the university lab with a sort of homemade wave winder, which wound this coil to get the right phase characteristic along the line. When they were made by Ferranti later on, they had a nice cover put over the top, okay? But that gave you a microsecond in roughly 6 to 7 inches. And this was a technique which also proved valuable to work at a microsecond in the serial circuits. We were conscious that Mark I technology would not work, and we needed something to work effectively at a megacycle. We decided not to go parallel in the rest of the machine, again for reliability reasons. So if you look at the delay line system, this shows you the sort of wave winding that went on, and this shows you the sort of signal that came out. This was the drive, 0.8 microseconds with a 0.2 microsecond gap, and at the bottom the sort of signal that came out after 10 microseconds delay. And if you strobe that with a 0.2 microsecond pulse, that was just about on to make a 10-bit register. And that was the system that we used. We had 10-bit registers. If you wanted to make 30-bit registers, then you clocked, you amplified and retimed, and then from the third slot fed it back to the beginning to recirculate. The other advantage of the Mercury, of the electrical delay line, was really in doing things like counters. Counters in sort of condenser memory technology were pretty grim, whereas a very simple technique with delay lines enabled you to make very effective counters. As you know, if you count in binary, if you take the first stage, it goes 0, 1, 0, 1, 0, 1. So if you put an inversion in a delay line which is circulating, then you know he thinks it's a 0, then he thinks it's a 1, then he thinks it's a 0, and if you do it with a bit more delay, it thinks it's 2 0s, 2 1s, and then it thinks it's 4 0s, 4 1s. So it was very easy to make very reliable counters, which we needed for addressing and for other jobs in the machine, counting the number of bits that had shifted to shift and so on. Also variable delays, so all registers, variable delays and counters, and this was a very economical technique and very reliable. And in fact, F.C. Williams maintained his interest to this on this circuitry stage, and all the circuitry, as it were, retained his characteristics of catching diodes and saturated pentodes. There was none of this double triode which extended through all America, let's say the least. I won't comment on this country, but we were all F.C. Williams type technology, and the valves were a bit smaller than in the Mark I, so these were miniature valves. That was a typical sort of valve, and we'd moved away from the thermionic diode to the germanium diode. So this was a move towards reliability and lower dissipation. In fact, there was something like 4,000 odd, 4,200 cathodes in the Mark I, only 1,800 in the Mercury, with 1620 crystal diodes. So even when you added the totals together, there was still less elements, about a 19% reduction in elements. So that was a move towards getting a bit of extra reliability, if you like. Even on our MEG, we had a look at transistors. It was a research student called Albert Nicholson who worked with us. There are 2 stories I want to tell about him. He clearly, if you have a valve machine with high voltages, you've got to protect your transistors because you've got to send signals between them, so protection was important. We went away one Christmas, and when we came back, 2 things had happened. He'd blown up a tremendous lot of transistors because he'd worked all Christmas. And the second thing was the machine didn't work either, the rest of the machine. And it took us a little bit of time to sort it out, but when I tell you that we shorted, on a memory tube, we shorted all the plates together at the back of the box, so there was only one spot on, and that's, instead of a small focus spot, what we saw was an annulus about 0.5 centimeter diameter. And this man had inserted a set of cathode followers which were supposed to achieve isolation. He'd not put any stoppers in them, and these were oscillating at a frequency we just couldn't see, and were picking up on the wires and going all the memory. So that was absolute disaster. So it took us about a week to recover from that, and a week to recover from mending his transistors. So in terms of the multiplier, we never allowed that mixture, as it were, of transistors and valves in the machine, and we got no further. We were looking all the time for improved components to use, and you know, this seemed a bit crude. And there's a man in Canada called Katz produced an adder tube. So we got an adder tube, and in fact we got a few adder tubes, but I've still got one, and that's it there. And the principle of it is very simple, and I'll just explain it to you. I've eliminated a few electrodes in, you know, to aid the discussion, but essentially the inputs, which were 3 to an adder, X, Y, and the previous carry, go on these electrodes, and the sum and the carry outputs are on these, and so all those sum electrodes are really connected together, all the carry electrodes are connected together. Now if you put an input which is a positive, say on this as a grid, this is the cathode, then electrons are attracted there. These are negative, so they're not attracted there, and they go through this mesh, which is here in the center, and they're picked up on the sum. So for any one input, you clearly get a sum output. When you put positives on these two, you've got to design the electrodes such that the majority of the electrons go through this gap. Obviously, the field is symmetrical one, and the electrons go through this gap, so it produces a carry and no sum. And of course, if you have 3 inputs, you want a sum and a carry, but then the whole field is symmetrical, so the electrons go out in all directions, and you produce a sum and a carry. Now, all I can report is that this tube, which is here, worked, but unfortunately only worked up to about 100 kc. So we had to throw it away and go in for, you know, the more conventional system. If I just talk about the machine a little, we used 10-bit words because that was the natural element that came out of the cathode ray tube. With the cathode ray tube, we had to regenerate the information, otherwise it would decay away. So in Manchester machines, there were things called scan periods when we regenerated the information, action periods when we could use the store to get something out or put something in. So we always had scan and action. Instructions were 20 bits, so we required 2 accesses for that. And of course, if we were using a 10-digit number, then you had a third action. So in 3 double beats, 60 microseconds, you could do arithmetic, if you like, on 10 bits, which was done in the B registers. In the MEG, we just had 5 bits to define instructions. So in a sense, in modern terminology, it really was a RISC machine. When it went to the Mercury, then we used, there was a spare 2 bits. We did go to 7 bits to provide extra instructions. And for example, the B registers, there were 8 in all on this machine. And in order that you could have something called a short accumulator to do sort of organizational instructions as well, which you could B-modify, then there was you identified B7 by a function code, and you were therefore able to modify B7 by the other B registers, so you could modify the address in the usual way, but to the short accumulator. So there were those sort of operations. Short operations were 60 microseconds. And if you went to floating point, where clearly you now require to get a 40-bit number out, a 30-bit fraction and a 10-bit exponent, then that took 180 microseconds. And multiplication was 300 microseconds. The type of multiplier was to take pairs of the multiplier to multiplicand, and we did this over 10 bits, so that you required 5 additions to do a 30 by 10, and then to make it economical, you did the same thing again for the next 10, and the same thing again for the next 10. So it was 3 lots of 30 by 10, and to, as I said, it was a pairs. We had to use one adder to form the 3D. So we used to take either 0, 2D, 4D or 3D and do the summation in that way. Perhaps I should mention here that something like the 701, a fixed point addition subtraction over 36 bits was 60 microseconds, but their multiplication was 500 microseconds. We were aware, and you see the Met comment about still paper tape, it said. Still valve. Well, looking back from 81, that's what they might have felt, but when you're actually at the time, there was really no option. But we were conscious of that, and in the period about 61, which is Mercury had been in and working, and in the period from 58 to 61 we were doing other work, and we looked at the possibility of producing fast magnetic input-output at the sort of order of 1,000 characters a second. I mean, paper tape was creeping up towards that 1,000 characters a second, but the output was still pretty crude. So we did actually look at that, and of course there's the other problem of could you transfer stuff from a keyboard to magnetic tape, and could you transfer from magnetic tape to a slowish printer. And at that time we were working on something called a static head, that is, something which could read magnetic tape even when it was stationary, and over a range of speeds, in fact. And we also devised this device, which was a double head, where you could write a digit, let's say about 5 thou digit, with a pulse applied to that sort of write head. When you moved it, you could read it with a static head here, such that you could read it and then say, well, you now know the digits move from this point to this point, and you can now write again. So in fact, on a control basis, we could actually write digits at about 100 per inch. Now 100 per inch in about 61 was about the standard on magnetic tape. In experiments they were going higher, but that was about the standard. ICI picked that up, wrote a specification in August 60 to make such a system, and subcontracted it to a firm called New Electronic Products. And in fact they actually made that system. It was installed at the ICI machine at Wilton, and we had a similar system at Manchester. But it's like all these things, you know, unless the users actually accept it, never really gets used in anger. And I think this was one of the systems which didn't really get off the ground to any extent. I mean, it was used, but in a minor sort of way. Now what I'd like to do is to just go through fairly quickly through some slides, and we'll have to go through Tom's slides first.
You can describe it if you like that one.
No, I'll go through them. I wouldn't have time to do mine then, and I don't think we should really go through in a delay. That's the prototype drum, yeah. Raster on the Mark 1. This is interesting because it's got ticks there. A man called Prince found his input unreliable, so he used to put it in twice on paper tape, right? One followed by another. If it was right, he used to tick it down the side. Brian Pollard and Keith Lonsdale on the Mark 1. Colour picture. Right, blank.
You're on your own now, Dan.
Right. This is the Mercury prototype. If you look on the wall there, we've got the Mark 1 prototype, Mercury prototype, the transistor machine, and some early work on Atlas. If you look at this, you see the chassis there look a bit neater than the original. Heater transformers on the top come down the side and in fact go into chocolate blocks on each side, so it's all done fairly neatly. You can't actually see this terribly well, but if you look here, each chassis is bent through a right angle, and there's about a 4-inch section sticking out there, and in fact there were lead throughs all the way down, so all the power supplies came down both sides here. And in fact at the back, all the connections between racks were put on tags strips which were down the back here, so you only had to loop them straight across. Now that was incredibly useful because this machine, if you see the lavatory brick construction at the top, was built on the same racks as the prototype, in the same room as the prototype, so you know any thoughts of keeping parts of that were absolutely out. The chassis were new, and in fact I've got the diagram which shows that the drawing office diagram at Ferranti's was May 1952, so they made us all those chassis to save us the metal bashing. and we were therefore on with building the machine from that time on. And this is the monitor display on that machine. And if we look at the next slide quickly, this shows the CRT stores on the Meg, 2 per box now, as opposed to 1 per box on the Mark I. And this, no Tektronix around in those days to produce you nice systems. This was a Ferranti copy of a monitor which came in the first instance from TRE, and that was the device we had to make it work. That's an overall view of the machine, again, as you can see, in the original prototype room. So that's the Meg prototype. We had to move that to another room. Oh, these are the delay line pulses. Instead of the diagram that I showed you, these are the real live signals, drive-in signals at the end of 10 digits. This was the construction that we made each 10-digit line in on the Meg. On the Mercury, they were put onto printed circuit boards and put into rectangular boxes, which is a bit more accessible. And this is then in the new machine room. So this is 1954. Now the interesting thing is, we used to get regular visits from the Office of US Naval Research and from IBM. Gentleman called Samuels, who wrote the chess program. He came in 1954 and we demonstrated the machine showing floating point. He was very impressed, and all we can say is, we've had no confirmation of this, but it's a good story, which is from that time the 701 was cancelled, and 3 months later they came out with a 704 with floating point. Now this is the Mercury as produced by Ferranti's. On the right hand side here were drum units which are not visible, but here is a graphical device which was built at the university and in a drum cabinet, in fact, to actually connect to this. Again, an attempt to improve the peripherals that we had, and that would plot. It was really a crude point plotting 2 points in about 120 microseconds. So you could plot 350 points without flicker, but on the back there was a duplicate tube with a camera which you could control automatically from the machine, and that could take pictures of what was on the screen. Now again, the basic hardware was there, but really for any user to use it, it was terribly crude. And we needed a lot of software, and it was one of the things that never really got picked up at Manchester. At other places it was picked up, and there were developments of both hardware and software, but we did struggle with graphics all the way through, and it never really took off. This is just to remind you of a core store. You can see the wires going through cores. I think in the Mercury system, the cores were 80 thou diameter, that's 2 millimeters. And of course the argument against the core in those days was that you could only get it 1 bit at a time. With with a CRT you got 1,000 bits. I remember Rachman coming to talk to us, and he was telling us about his plate, which had 1,024 bits in a ferrite plate. But if you think ferrite shrinks something like 20% when it's fired, those plates always cracked, and I don't think really they got more than a few to actually work in their entirety. This is the drum cabinet. Another sign of the times, the modules at the top are plug-in modules from Pegasus, really, design, which was another machine going at the same time as Mercury, but of less performance, and designed by Ferranti themselves. So that's the drum cabinet. And in conclusion, just show you the CRT. In our case, this was 6 inches diameter. On Mercury, that was 1K bits. And just to sort of bring us up to date, that's a megabyte. So that's a factor of 8,000, okay? And you can see the scale. And of course, you had the KV and the delicate nature of vacuum and so on. So I just think that puts us in perspective of where we were, as it were, with Mercury. Thanks very much.
Thank you very much, Brian. We've got time for a question to Professor Edwards. Anyone like to ask a question? Can't see up there. Are you all still away? Oh yes, there we are. Gentleman at the back.
What's the course score that was used in the Mercury, the first application of that technology, or was it adopted to do this experiment?
I'll ask Alec to do that. I mean, as far as I understand, it was a system which was designed really to go into Mercury. But I mean, he might have some other ideas. It was the first time for Anti had put them as things, as far as I'm aware.
I don't think I was at the Anti. I was just first in touch with the work at the university. I know that they made the prototype for Mercury. As soon as we took over the work, we started working on the course score. So I'm not really anything. I don't think ever produced calibrated clocks and Mercury.
No, they did.
They did for my prototype.
Yeah. No, I mean, that was a decision to change from the CRT as soon as you were making Mercury.
Yes, that's right. Does that help?
Thank you. Another question here.
You were saying that the Mark machines were communalized. Yeah, they were used quite professionally by aircraft companies and Mark 1
What we're saying is this: it's the frame of mind that you're in, right? And if you're a user like the crystallographer who was wasted 250 hours out of his total, right?
Yes.
That's 14%. That's unreliable. If also he couldn't get at the machine for 10% of the time because it was his maintenance time. You know, in terms of using a PC currently, you know, that's unavailable time, right? So it does depend on your frame of mind. Now, what the crystallographers were saying is, we use these machines despite that significant time loss very effectively, okay? And of course, all one can say is, perhaps we should be using PCs much more effectively.
Because, I mean, our wings on these machines.
But see, I think the essence was, with electronic equipment, if it's television, for example, or radar, you could give it a kick, and it would work again next time. But if you did that to a memory, then unfortunately that was a disaster, because it filled with bits. I mean, there's a story that I could tell. When we moved the machine, our prototype, from Dover Street, from the original building in Coupland Street to a new building in Dover Street, it was on the top floor of the new building, and we just installed it, and all of a sudden we started getting bursts of digits put into the store, and we slowly realized that these were coming at a regular rate. And then we found that Smith's Aviation were testing a radar to destruction about a mile away, right? And so what they did was to beam the radar right onto us, and we screened the appropriate bits, and there were no more problems. But it shows you the sort of
I worked in AVO in Manchester, and they actually built a completely copper screened room. The whole room was, the machine was...
Well, our room was built with chicken wire. And part of the difficulty is you don't know how well the connections were all made, but we certainly had grills over the window. But the radar, a sort of half a mile away, came through it like nobody's business as far as the memories were concerned.
Highly programmed. If I may use the Mark 1 Star Wars made sure that they'd made some progress, so that if they had a long program and the machine went down towards the end of it, they made a lot of progress which they could refer back to, and it was not everything. But this was a student on the program.
Well, I think you know what you're talking about are the sort of people we like to hear about, but there are always other sort of people who want another factor of 2. You know, it will run reliably for 20 minutes and you'll have no problem, but they want 40, and it's absolutely essential, right? And of course, in some sense, it's good. You know, it's a hell of a bite at the time. it's really good because they put a different emphasis on things. And again, you see, people want faster machines. We like it twice as fast because I can't do anything unless it's twice as fast. And it does make you think and make you strive, really.
Right. At that point, I can see Dick Grimstone getting ready to talk. So I've got to be brutal with this discussion. Thank you very much, Ty. I'm sure there's opportunities to meet all of the speakers over lunch and coffee. So our next speaker is Dick Grimstone. Without delay, Dick, off to you.
I just thought I'd set the scenes for the early 1950s. And we had the appearance of the called the crystal triode by SDC. That was our main source of these devices, and it's already been mentioned that Barry Chapter and F.C. Williams were doing some experiments on using these devices. A bit more of the data sheet. We could look at these again later if anyone's interested. Here's the outline diagram, but what I've done here is to show what's inside. So here, as far as we know, inside was the germanium slice, which was a single crystal, purified germanium slice, slightly doped with N-type material, and these two cat's whiskers. There had been early experiments before the war in trying to control the flow of a crystal, a diode, with an electric field. But it wasn't very successful. These devices, no one quite knew how they worked. There was various theories, but what you had to do is you had to set them off into action by doing a process of forming, which was to take a 0.1 microfarad condenser, as we called them in those days, charge up to about 20 volts, and discharge it between the base and the collector. And that made it into a transistor. We previously had valve flip-flops, and they needed an emitter follower. And here we have one of the EF50s, not an original one. How do we make this work? Do I have to start it?
You just have to press that one to move on.
Okay. Right.
You find it at the back.
There we go. Rather faintly, so we've seen this better, but we had about 3 of those valves in the flip-flop. By way of comparison, here we have the circuit, the basic circuit of the transistor pulse amplifier. Now, the remarkable thing about the point contact transistor, it had a current gain of greater than unity, an alpha greater than unity. That is, the ratio of the collector to the emitter current was greater than unity. As such, it had this negative impedance characteristic, and you could make a 2-state device out of this one transistor. I'll try and explain very briefly. When it was off, there was a little bit of base current, leakage current flowing in the base and the collector, and something in the emitter as well. So the emitter was hooked on that diode, and this was down at -12. Although it was a triode, it had pentode-like characteristics, so it obeyed the F.C. Williams rule. The base was held slightly above the emitter, so this junction was off. What one did is push some current into the emitter. That caused a greater current flowing in the collector, say 1 milliamp in the emitter caused 1.5 milliamps in the collector. This caused the base current to flow, which took the base down and caused more current to flow. So we rapidly got an avalanche effect, and the device turned on. But of course you had to turn it off and I missed that out of the slide. So that's the turn-off waveform. You had to take the bass up to turn it off. So there we had a replacement for the flip-flop, leading to economies. That sounded all very nice, but some of them were a bit variable. So the cycle time here, we have a 4 microsecond on, 4 microsecond off period, and we had to make fairly good use of both times. If we're lucky, we get a reasonable turn-on time, and then they were fairly difficult to turn off because the conducting elements, not electrons but holes, had a habit of hanging around, and you had to coax them out by dragging them out of the transistor to get the transistor off. So it took some time to get them off. Some of the transistors, however, didn't seem to want to go on at all and were very slow on turning on. So we had to look at quality control, and these were results from batch tests of various batches, and it was very depressing when you got the second big batch came along from SDC somewhere in the pool area, I think it was, down there. These were very bad. They worked. If they're in this region, they worked. If they're in this region, they need a lot of current to get them on, and if they're in this region, they need a lot of current to turn them off, and these didn't work at all. So we went on then to make the basic circuits, and I'll flash through a few of these. Here we have the AND gate. By adding diodes here, we have the AND gate. Here we call this the not equivalent circuit. We use this symbol, exclusive OR, and that was a half adder. So we had three. How many transistors? Yeah, two transistors there for the half adder, because we also needed circuits for the carry as well. And we could also do the timing circuits as well. And I think this board, as far as I remember, is in fact a 4-stage one of these. This is 2 stages, and we generated waveforms by storing charge here. So this circuit set up some charge here, and this went on, and then when we pushed it round, it's a shift register type circuit, because that was on, it caused that to go on and then charged up that capacitor. And here we have the 4 stages, and here we have the point contact transistors, various diodes here and there, and the capacitors. And I'm going through these quite quickly just to show you 1 or 2 circuits. No attempt to explain them, but here we have some waveforms as well. So there we are. We've got some of the basic circuits of the machine, and from this we're able to make the prototype computer. And this was, as been said before, uses the magnetic drum because it seemed to be the only one, only storage available. We try to avoid thermionic devices as much as possible. So there was no thought of using a cathode ray tube, for example, but we must confess we had to use some valves in the read and write amplifiers. The feature of this also was that we had these so-called regenerative tracks. So these were a delay line type store, but the delay was created by the drum revolving, and the information was recirculated around through the this loop, and there was about 1-digit delay there, and we had about 10 digits delay per syllable. We used a 48-bit word on this machine. The other feature was with the drum, of course, we could have all the timing waveforms stored on the drum. So we had a clock track which had 3,072 pulses per rev, which was 64 times 48 bits. The word length was 48 bits. We had 4 spare bits per word for timing and 44-bit words. I'm not quite sure why we chose 44. We had to write this clock track. Writing this clock track was a very skillful process. It had to be done early in the morning or late at night when the mains were very stable, because we had to get exactly 3,072 pulses around the rev, and they mustn't overlap at all. We had a very skillful technique for adjusting the position of the heads. This was a nickel-plated drum, and to set the spacing of the heads between the drum, and the drum had a very slight eccentricity. It was very good, but it's very slight eccentricity. So you adjusted with a little screwdriver, wound the head in until you had a little ping, and you quickly wound it out again before anything rather drastic happened. And the clock was 125 kilohertz. These are the heads. We used to make some of these heads ourselves, and with radio metal. And at this stage I might perhaps refer to Doug Webb, who was my colleague. Doug was quite a character. He Canadian, and he was a great Bugatti enthusiast. He also invented the Trojan Oscillator. He had one of these Trojan cars, which is highly sprung, and it had it's belt driven and a reverse lever on it. And Doug used to stand with the car engine running and hold the gear lever. It was outside the car, and the car used to oscillate backwards and forwards as the gear lever moved in his hand. And here we have the programming manual of the prototype machine. The early machine we've heard about with Tom and Jeff Tootill, I think only had a subtractor, but we didn't see why we should be so Spartan as that. And as we got the adder and the not equivalents more or less for nothing, we didn't include these. And it was micro-programmed because we had individual bits to control the various gates that did the various operations. I kept a notebook in those days, and I've put an overlap of two adjacent pages. Unfortunately, on the first page I wrote 16th of November, machine first operated automatically, but fortunately on the page opposite I put the date 27th of November 53. So as far as I know, and I think Simon perhaps can bear this out, this is the first transistor computer in the world to operate. It started in late 1952. It had 92-point contact transistors in it, and there were about 6-point contact transistors, 6-point contact diodes on average for each transistor. We then decided to take it to pieces and build a bigger machine, and perhaps before I go on to that, I think I've got a couple of slides of the... There's the prototype. Again, this was upstairs from the lavatory tiles. This is a room upstairs. We had to build our own oscilloscope. It was a Cossa, but we had to add all sorts of bits and pieces to make it trigger and do things like that to it. All rather untidy. And here we see the drum down here and some more of these racks. F.C. Williams once remarked how thin this machine was, and there's a better picture somewhere else. Tom did make a suggestion at one time. He said, why can't we make everything so very small, suggesting integrated circuits? But of course we couldn't make it small because we had to have good access to it, because it was so the transistors were so unreliable. I'll talk about that again in a minute. Here we've got a couple of circuit diagrams of the multiplier. So this included this full-scale machine included a multiplier. So perhaps I better go back and show you this machine again. What effectively it was, it had now had a B register with that was an 8-word serial register, which was used not only for the typical instruction modification, but also as a more rapid access memory. The main store was here, and because we had to align the main store with any one of these 8 words, we had to have a single word temporary register here, so we could shunt words into the correct place in this B register. And there was a multiplier in this machine as well. And the regenerative tracks had a delay of either 1 word, 2 words, or 8 words. With 1 word, the the write and read heads were about ½ an inch apart, and we had quite a lot of difficulty in making sure there was no direct coupling between the write heads, which carried a fair amount of current, and the read heads, which picked up a very diminutive signal from the drum. We had many things to plague us. The drum was one of these prototype drums, but I think it was a reject which someone let me have, and it had a hairline crack down it over certain parts of the drum. So it was fairly difficult to try and position these regenerative tracks, because if we hadn't gotten them on a clear, a good part of the drum, then as the hairline crack went round the under the heads, it would pick up a stray bit, and we get this single bit error appearing in the word. Well, this machine was operational in 1955. It had 250 transistors. The power consumption was 150 watts. It had this automatic multiplier, and the product of 2 44-bit numbers to give a double-length 88-bit result was 1.5 drum revolutions. The drum was 3,000 revs per minute. It had a surface velocity of 90 miles an hour, which always rather terrified me in case it was going to explode one day, but it didn't. Division subroutines were 1 second, square root 1.3 second. And we had a 1+1 code, which we did use for so-called optimum programming. So the instruction had the address of the operand. It also had the address of the next instruction. And we tried to arrange by careful programming that we could get about 3 or 4 instructions in each revolution, so that the drum was just going past at the right time. The problem with the machine was the reliability of the transistors. So here is the full-scale machine, and that seems to be almost printed as a negative rather than a positive. Had a control panel here. The output device was just a row of little fluorescent tubes. Here is this monitor, an improved version of the one that Di showed earlier, but I thought when Di mentioned the monitor, we had to be fairly fit in those days because we had to lug these things around the machine to get to the various parts of it, particularly with the Mark I. Here's the drum, and here are these tag strips, and that one which I showed you is probably about there. There's a better picture of it on the wall. It's a close-up of these tag strips. I was reminded that we called these tag strips. Power distribution here. We did have a minus 50 volt line on the machine to give a good pull down to catch against the minus 12 collector catching diode. Here is a Mullard point contact transistor, and the others were the SDC. And another close-up of the control panel. We had to deal with, attend to about 2 transistors every week became defective. In fact, I think it was rather worse than that. Nearly every day in the morning one had to find out whether there was a transistor stuck on, and we had to add extra base resistance here, resistors, to pull the base, hold the base off. Otherwise these things were stuck on. We used to think this was probably due to ingress of moisture. One or two other things that we did at that time. The drum made use of relays generally for selecting writing heads, and we did some work with saturable transformers here to do a selection tree, which actually did work. And then we came on to the advent of the junction transistor. And if you remember that we had a 4 microsecond period for turning these on, these were rather slower and also quite slow to go off, so they were didn't seem to be very attractive. Nevertheless, we did a core store, made a small core store with these, and that was a complete little sort of microcomputer with core stores and ladder. That's the right amplifier and the read amplifier. Round about this time, Willis Jackson, became Lord Jackson, who was the professor, I think, before F.C. Williams, came along into the little room where we built these machines and said, I'd like you to take 2 apprentices from Metrovic, Peter Clute and John Bailey, as part of their apprenticeship, and work with you on this machine. So I did this, and the long outshot of that was the commercialization of this machine by the then Metrovic's company. Became the Metrovic 950, and this machine was built, and I think about a quantity of 7 of these machines were built, but it was they did decide to go to junction transistors because they did appear to be rather more reliable. Here's a bit of program that appeared in that instruction programming course. It seems to be calculating some function which is 0.1 of sine of the square root of the mod of sine theta. Now, quite why anyone should want to do that, I don't know, but that seemed to be one of the standard library subroutines. But to trace a little bit of history as well, they were also thinking about commercial applications. And I was also associated with the 1010 computer, which they built later. And although this was the 950, you see mention of sort of commercial sort of applications here. The 1010 became the first commercial computer to do multi-programming. And later I added an interrupt to make it to the 1040, which became a process control machine. But finally, I think we just have to cast our minds back to those very uncertain days. We were all very uncertain about things in those days, and we had to push things quite hard. And I'll leave you with that quotation.
Thank you very much. We've got time for a question or two.
Actually, I forgot to the last few slides. This is the 950. Notice the ubiquitous paper tape read and paper tape punch. The drum, a circuit board, and the other side. And is there one more? Yes, the close-up of the control panel. Being a power engineering company, they like to show have a meter on the front to just see how it was running. It's quite useful to show if something went wrong. I think some 7 of those machines were built, and they were used throughout the various branches of the company, and they were about as powerful as a modern pocket calculator.
Thank you. Questions? I see a hand raised there.
Yeah.
I was thinking of something that Tom Kilburn said, and also that you said, about how people never thought anything could happen. Because I was at MPL, and therefore that was in the civil service, and therefore there was a civil service committee which had, I think it was about 49, all the way round. And I was stupid enough to write a report saying that I thought that there would be a future for computers. Firstly, because there'd be commercial use at one time or another, and secondly, I suggested that magnetic tape, which is used for all sorts of other purposes, would be very useful. So I wrote this report, and I was really, told how absolutely stupid this silly sort of idea was. There was only going to be one computer anyway, at least there was going to be 5, and that was too many.
I have one question. You mentioned the 1010 was the first machine to do multi-programming. Did it include any technique for ensuring that an error in one program could sabotage the others?
There was no, probably not, but there was some recognition of synchronization in those days, but with hardware. Sorry, this is not the answer to your question, but there was, I do recall, some recognition of the importance of modern synchronization techniques associated with handshakes with I/O. But this is a different issue, and it wasn't generally recognized that you had to have a correct handshake to ensure correct operation. No, I think the things did work, but there was always the danger that you could get an incorrect interaction between the programs. But I think the programs were fairly simple and were written with much labor and love. But I just remember a story about the trials and tribulations in those days. They sold 2 of these 1010 computers to the RAF at Hendon, and of course there were the dreaded acceptance tests, and the acceptance test required that should be so much work done in 24 hours, and this machine, they struggled for about 3 weeks to try and get it to do the required work in 24 hours, and in fact it took something like 24 hours and 5 minutes and they wouldn't pass it. That they were completely inflexible. They said 24 hours it's written down and 24 hours it should be. And the company nearly went out of computer business because of that. The directors said, we'll finish with these computers. We're not in our business at all. And this total inflexibility nearly killed that line of business.
Right, thank you. Thank you very much, Dick. This is now time for lunch, and I have some complicated instructions for you, how to get from A to B. When you leave this lecture theatre, head for the Space Gallery, walk along the underbelly of a white rocket, and you will see some escalators. And as you get to the top of the escalators, half right is the tea area, chairs to sit down, etc. Since this is an up-only escalator, on the way back, unless you're feeling very fit, the thing to do is to go down some stairs and find your way back there. A couple of other announcements. For the speakers, there will be a team photograph just outside the lecture theatre at 1:15, i.e. a quarter of an hour before we reassemble again for lunch. I've managed to find a quotation in answer to the very first questioner who asked who said that there would be only one computer in the country. Well, in September 1951, Professor Douglas Hartree told Vivian Bowden, later Lord Bowden, as follows. He says, we have a computer here in Cambridge, there is one in Manchester and one at the MPL. I suppose there ought to be one in Scotland, but that's about all.
Can I just cap that? I remember Lord Bowden, who used to sell the computers for Ante, said at that time that it was rather like selling lighthouses. You didn't sell very many.
Tom, did you want to say something?
Yes, you talked about photographs of the lecture.
Yes.
There are some very important people who contributed to Manchester Computers here, as well as those who are actually speaking. Can we have a second photograph? Including all those people who care to turn up for the photograph.
I think that's a very good idea. Well, thank you very much. We resume again at 1:30 sharp.
Thank you.
Well done. Very where did I get these photographs? I know that. I would have them in the yes. Well, one day we'll have a second
Have you finished with that, Dick? I'll show you.
Yes, okay, yes.
Thank you very much.
Have you seen the size of that? I had to bring a suitcase to bring that down.
I'll borrow it again because I've got to give a talk in Germany next year.
Well, next year? You don't want to take it with you?
I'll take it with me if you like, yeah.
Hmm?
Yes, I'll take it with me.
Do you want to take it with you?
Yes, yeah, right.
You know, you talked about a 50 volts.
This is a multi-programming. No, that was the thing. No, it wasn't the first. No, it wasn't the first commercial computer. It was the first one to do a multi-program. Oh, that's what I thought. He has a commercial to do as well. Right. If it didn't have any protection,
I mean, I can imagine at the top. Mechanically, they're
it didn't have any protection.
That means that's delivered to Manchester. I mean, I was amazed. I mean, I just This is the